Good afternoon, everyone. I will continue to introduce the metrology activities for the structured surface of ProSurf. And my presentation today including the following parts, and I will introduce the offline surface alignment and the feature-based surface characterization, and then followed with how to show some new progress on our machine surface alignment and with a brief summary of the work I've done in ProSurf. And nowadays, with the increasing manufacturing capability, which Lars has shown in his presentation, surface can be modified and structured to achieve specific surface functionalities. And the micro and nano structured surface is now actually driving the functional surface innovation. For example, high aspect ratio structures for the surface dry, for the dry adhesion, and also there are many hydrophobic applications, and anti-reflective optics can also be used in cars and glass to improve the visibility when driving at night. And it can also be used to increase the efficiency of solar panels. And even our daily shoes today are developed with skin, with a slick skin structure for better drag and friction management. To address link between the surface geometrical specifications and the function performance, in ProSurf, offline surface alignment procedure was developed with identified indicators for surface functionalities as summarized in this table. And for example, in ProPat, cohesive scanning interferometer was used for both remote insert and repeat surface alignment. And the depth, width, and spacing of the V grooves are used as indicators for the surface functionalities. And an important notice here is that due to the complexity of the surface structures, a variety of alignment instruments, or we can call it multi instrument alignment, need to be used to measure different kind of structural surface. So we can get full information of the structural surface. And more detailed information of those demonstrators, I think, will be reported in the later presentation by Nas. Indeed, actually, it is the surface features that determines the surface functionality. And the components that contribute to a surface texture include the size and shape of features, its aspect ratio, and distribution of features, and its hierarchical arrangement and the orientation of features as well. And through this ProSurf project, we gradually noticed that surface texture field parameters might not directly link to all surface functionalities in some cases. So a typical example here is the surface roughness. The surface that have the same value of surface roughness, but might different in the surface features, and thus result in different surface functionalities. And in this project, a surface feature spectrum was proposed, and the surface can be classified into stochastic dominant surface and the deterministic dominant surface and the surface features between them. The demonstrators actually developed in ProSurf actually cover the full range of the feature spectrum, and most have deterministic features or stochastic and deterministic features. And based on this spectrum, a new set of surface calibration tools named the feature-based calibration are developed and present in the following definition. It means the analyze and the calibration tools operating on identified surface features and their associated analytics. And here is the framework of the whole process. And after the leveling and denoising of the surface memory results by different surface filtrations, and we can obtain SF surface containing the features and structures. Then followed with edge operation, thresholding, or other segmentation method, the surface can be decomposed into features and their relationships. Then the feature parameters can be calculated and used for more detailed data analysis and linked to its surface functionalities. The picture shown on the right-hand side is a simple example of how to use this method to get the information of each individual lens and their relationships. As you can see, after denoising royal alignment results. The segmentation operation can be used to build a change tree of the surface, and each length can then be calculated and its future attributes, for example, error and its maximum, and also more detailed information can be calculated and summarized in the table. More detailed information can be found in the CRP keynote paper this year, and also a book by Professor Zhen Tong and Paul Scott, which are available online as well. Another challenging in mass production of high precision functional structure surface is the iterative nature of offline alignment, which bring actually a huge effort, time, and cost associated with the whole processing chain. To achieve the fast quality control and improve the efficiency of the whole process chain, there is actually a trend of shift from offline to online surface alignment. And in ProSurf, on-machine surface alignment and all in-process monitoring technicals have been developed for each advanced machining and also replication process. For example, they are including the fast-to-servo process and the micro ETM, injection modeling, and the roller cleaning process as well. And embedded sensors has also been in-house developed according to the requirements. And due to the time limitation today, I will focus on the integration of embedded sensors into auto-precision machine tools and with some typical examples. The on-machine surface alignment is not just mount a sensor into the machine tool stage. Actually, here are mainly three things need to be carefully considered. The first question is how to select the proper sensors. Actually, in generally, the sensor to be small and performance stable and capable to capture the surface features of interest and has high measurement rates and also high data precision speed. And for our ProSurf applications, single point alignment sensors offers the best feasibility, and we have tried both a traumatic confocal sensor and an in-house developed dispersed in a reference interferometer sensor, and integrate into the machine tools for both freeform surface machining and structural surface machining. And the next stage, after you find the right sensor for your application, the second question is how to integrate and realize on-machine surface alignment. And to make on-machine surface alignment results compatible with the offline alignment results, the whole system need to be calibrated carefully in the machining environment. And this actually includes the motion error, calibration, and also the sensor repeatability, linearity calibration in the machining environment. And also we need to carefully design the scanning strategy to minimize the effect of misalignment of probe, and also the vibrations come out from the system. And after that, after integration and calibration, the next step is how to control the data flow to close the loop of both the freeform of the machining and the surface alignment. To control the whole process, a controller was developed for the data synchronization and the data precision. Here is the whole framework of the developed fast-to-servo machining and on-machine system with 4 functional modules. That means the fast-to-servo machining and on-machine service environment module, and on-machine error compensation module, and on-machine service calibration module. And the control panel, as shown on the left-hand side, the control panel was developed to control the whole process for both the machining and the surface alignment. Some highlights of the system integration here is feature-based point cloud two-pass planning is more suitable in this case. And at least at this moment, we found this most flexibility method in this closed loop machining and on-machine alignment system. And the fast-to-servo structuring technology using the point cloud has been developed, and we can achieve 10 million points to generate different kind of structure surface or freeform surface. And this I think is at least 2 times better than currently company, which can be offered by company. And then secondly is that based on the error map from the on-machine surface alignment results, And our machine error compensation module was developed to further improve the form accuracy of machined freeform surface. And this technology we have demonstrated currently on our Precitech machine of 10 years old, but the technology is very fully transferred to other auto precision machine tools as well. Okay, and then next I will show some case studies that based on this closed loop fast to servo machining and alignment platform. To verify the on-machine surface alignment and on-machine error compensation module, two typical freeform surface was designed, a length array and average length that has a focus variation function. And here is the configuration of the machining and on-machine alignment as you on the left side. And the video here, yeah, showing the on-machine surface alignment, yeah, in the real time. And you can say during the after machining, we can do the scanning, and the result can be shown in real time by this method. And once we got our machine surface alignment results, an error map can then be generated, and without moving or changing the OPs or tools. And then this can be used as a compensation value in corrective machining if their form error is larger than the design specifications. And from the measurement results, we found that after composition, this method actually can significantly improve the form accuracy of the machine freeform surface. And our newly progress indicate that this can bring down the form error down to near 150 nanometers on this old machine. Yeah. And more detailed information can be found in our newly published paper in CRPI News 2021. And also offered by the high flexibility of on-machine surface alignment, we also managed to do quick cutting to change during the machining process, and also this enables us more flexibility to generate structures on freeform surface. And with the surface feature-based surface calibration method, we can extract the features of each length and analyze the V grooves generated in the length arrays. And detailed work has also been reported in the CRPI News 2020. And in the next few slides, I will show how the developed feature-based surface calibration method can be applied in different structural surface. The honeycomb is a very typical periodic structural surface. As shown in the left-hand side, the design surface can be well generated by the design feature-based fast-to-servo machining system. And after watershed segmentation and wolf pruning, we can obtain the detailed features as listed in the table. And also, we're using the arrow autocorrelation function to analyze the native structure of the pattern. This actually indicated distributions, for example, the spacing and the pitch value of the pattern of the structure. And tessellation is another typical functional structure surface. As Lars has mentioned, the VSTS machining can also generate this kind of structures on surface. And with the developed feature-based surface structure design and two-pass generation module, this kind of patterns can also be generated on and can also be generated with very attribute distribution. And the segmentation method can then be used to analyze each features, and the surface defect, structure defect of this radiant line can be fast identified by the analysis of feature error information. And also arrow autocorrelation function can also be used to analyze the distribution of radiant features. This detailed work has been included in the emerging leaders connection of surface topography 2021. The last example is the biological structure surface. And snake skin is a very typical surface for drug and fraction management. In a different area, actually in the scale on the snake skin has different functionalities. And the proposed feature-based surface calculation method can identify each skill and the near detailed feature properties. And ACF analysis also can show the local periodic information of the skills. Well, here is a brief summary of my talk today. The arrow, texture parameters, and the geometrical indicators that are suitable for the assessment of specific structured surface in ProSurf has been developed. And the core technologies of on-machine surface environment has been developed and demonstrated in the diamond machining environment. And a closed-loop feature-based fast-to-servo patterning and also surface calculation method has been developed and verified with typical freeform and structured surface. And the non-stop manner of the developed closed-loop fast-to-servo machining and the on-machine surface environment platform can significantly improve the machining efficiency and also allow more complex freeform surface to be designed and tested with short lead time. And taking this opportunity, I would like to thank you the funding support received from the European ProSurf project and also the support received from UK National EPSRC Future Metrology Hub and expertise support from Ted Hobson and the contributions from my colleagues. Thank you for your attention and any questions.